Okay, let's expand maybe our set of prototype examples of what a linear program can look like. And so in this video, I'm going to introduce another prototype of a type of linear program you might try. And yeah, a lot of realistic scenarios sort of fall into this category here, which is a scheduling problem. And they can become much more complex and involved in real life with real life scheduling problems. But this basic one should introduce us to a lot of the subtleties that come up with designing a scheduling problem. So pause the video, read through it, see if you can identify what the decision variables should or could be. This is probably the number one trickiest part, is choosing appropriate decision variables. Okay, so let's kind of talk through this problem and discuss what we'd use for our decision variables, which will then determine our objective and constraints and everything else. The key here, and this is the key for most scheduling problems, is that by choosing a clever choice of decision variables, you can essentially eliminate some of your constraints just by how you design your variables. And so if I'm reading through this problem and sort of identifying things, we've got different number of employees required on different days. So each of those is likely going to be a constraint. So we got only full-time employees. That sort of limits the scope of things. But then we have this union rule. Union rule states that each full-time employee must work 5 consecutive days and then receive 2 days off. And so that at face value might seem like a constraint. It is definitely something that limits where we can put our workers. If we didn't have that constraint in there, we could just have our decision variables as the number of people working each day of the week, right? And then we choose exactly this many people for each of those days, right? Problem over, very simple. The challenge is that we need to satisfy this union rule. And the trick is that instead of setting up that union rule as a constraint, we're actually going to bake that union rule into how we set up our decision variables. So let's talk about a choice for our decision variables. So instead of having our decision variables being the number of employees working on a certain day, we're going to focus on the fact that union says that they can only work 5 consecutive days. And so essentially your choice is not how many people work on this day, but when should I start each of my employees on their work week for their 5 consecutive days. So once I start them, I know that they're going to work the next 5 days. And so my first decision variable, I'm going to call that MO for Monday. And instead of being the number of workers working on Monday, that's going to be the number of workers starting Monday. And so then they work Monday to Friday. Okay. And so by making that decision, that bakes in the union rule in that all these workers starting on Monday are going to work a union specified work week. We'll repeat that for the other days. So Tuesday are going to be the same number of workers, and these are going to be the workers that work Tuesday through Saturday. Wednesday works Wednesday through Sunday, and Thursday, Friday, Saturday, and Sunday. And each of those will work Thursday through Monday, Friday through Tuesday, Saturday through Wednesday, and Sunday through Thursday. Okay, sorry, missed the end there. Okay, so those are my decision variables. Is essentially they're the number of workers starting on that day and working 5 consecutive days. So What is my objective then? Well, I want to do it, I want to satisfy the staffing requirements with the minimum number of full-time employees, right? And so essentially we're minimizing payroll and we're assuming that everybody's paid equally. And so we can just minimize the number of workers. And so my objective is now going to be a minimization problem. Okay, we've dealt with maximization problems. Here we're minimizing a cost, which is employment cost, while satisfying that we need to meet some staffing requirements. So we want to minimize the total employees, which is going to be the Monday workers plus the Tuesday workers plus the Wednesday starting workers, plus the Thursday starting workers, plus the Friday starting workers, plus the Saturday and Sunday starting workers. And so each of these decision variables is workers starting on that day. And so the total number of workers is just adding up all the decision variables. So now we can move into our constraints. Okay. So for our constraints, we're going to have essentially our staffing requirements for each day of the week. And to kind of set up those constraints, we need to think of, okay, if these are my decision variables and they're tied to which day they start, who's working on Monday? And so we're essentially going to get a constraint for employees on Monday. And I got to think, well, who's working on Monday? And whoever's working on Monday, I need at least 17 people. Okay, so if you start on Monday, you're working on Monday. If you start on Tuesday, you're working Tuesday to Saturday, and Monday's actually one of your off days. So we can kind of skip Tuesday. Wednesday, workers have Monday as an off day. Thursday starting workers work through Monday. And so Monday plus, I'll actually leave a gap here and jump over to Thursday. And so you can think of it as there's no Tuesday workers and no Wednesday workers. But then Friday, Saturday, and Sunday workers are all also working on Monday. And that has to be at least 17 workers. So the total workers working on Monday, that's what this expression represents, must be at least 17. We can repeat it for the other days of the week. And so I'll maybe do a ... Well, here, I'll do one more and then I'll do the ... So employees on Tuesday. If you start on Monday, you're still working on Tuesday. If you start on Tuesday, you're working on Tuesday. But Wednesday and Thursday workers are off on Tuesday. And so then I get Friday, Saturday, and Sunday workers. And that has to be at least 13 workers on Tuesday. Same scenario for the rest of them. I'll do the last one as well. So employees on Sunday. For Sunday, we've got Monday workers and Tuesday workers are off by then. And so then it ends up being Wednesday plus Thursday plus Friday plus Saturday plus Sunday workers that are working on Sunday. Okay, and for Sunday, quieter day at the post office, we need 11 workers on Sunday. Okay, in addition to these constraints, these are our functional constraints. We'd also have our non-negativity. We can't have anti-workers, as much as some workers might have a bad attitude about being the people that are working over the weekend. They don't count as anti-workers. And so we'd have that the Monday workers has to be greater than or equal to 0. Same with the Tuesday workers has to be greater than or equal to 0. All the way through our Sunday workers has to be greater than or equal to 0. Finally, we need full-time workers, right? We're not allowed part-time workers. And so in this case, we'd also have integer variables. And so you can think of this as sort of a specification on the variables, or a constraint of saying, we've got this constraint that we're constrained to only have integer values for our variables. And so this violates that divisibility assumption of linear programming. And so we'd actually have to use integer linear programming. Though I will say, in certain special cases, you can get by just crossing your fingers, and that sometimes when you solve your linear program, you end up with integer solutions. And if you do, then they're the optimal solution, and you can go with it. The tricky thing happens when you, if your linear program would come back and say, we want 10 and a half people starting on Monday. That's not going to work in this setup. And so then you need to figure out what the optimal integer solution is. And it's not always the closest solution that you would get by rounding your answer. So often when you round your answer, you're going to end up outside of the feasible region, because remember, our optimal linear solutions are right on the border, or the corner points of that solution. And oftentimes rounding will take us outside of it. Okay, so scheduling problems, a really valuable prototype that a lot of linear programs fall into.